Hi everyone. We're going to continue on in Unit 5 with the derivative of the exponential, e to the x. And you can see the objectives here. I hope you'll write these down in your composition notebook. And again, as we go through each one of the examples, remember that you're using the examples to learn the material. All right, so let's get started. Okay, so the derivative of the natural exponential function, the derivative of e to the x, is e to the x. Or if I take the derivative of e to the u, it will be e to the u times the derivative of u, du dx. Okay, it's my favorite one, so easy. All right, so geometrically speaking, I don't know if you can read this on here, but it says that the slope of the graph of y equals e to the x at any point x e to the x is equal to the y value of the point. So what that means is that on the graph of e to the x, the derivative, which remember is the slope of the tangent line at any point, is the same as the y value on that graph all the way up. Kind of interesting. That's why the derivative is the same thing as the function. Okay, so let's do the first example. Y equals e to the 3x minus 5. So if we want to find the derivative, we do e to the 3x minus 5 times the derivative of 3x minus 5, which is 3. Now you'd usually write it like this so that it doesn't get caught up in the exponent. Okay, so here what we have is we have y equals the natural log of e to the x. So if I rewrite this using the power rule, I have x times natural log of e. Well, we know that the natural log of e is 1. So if you take the derivative of x, you get 1. So in this one, we have two examples. The first one here is y equals e to the negative 7 over e to the x squared. Okay, so what we do here is we go ahead and we take the derivative. And remember that it's the same thing, negative 7 over x squared times the derivative of the exponent. Now, I'm going to write this down here just so that we do this. This is negative 7 over negative 7 over x squared, which is the same thing as negative 7 times x to the negative 2. So if I take the derivative of that, I'm going to have 14x to the negative 3. So that's going to be 14 over x to the third. Okay. And you can switch the order on that if you want to. Now this next one is really interesting. It looks really difficult. I love logs for that reason because they look harder than they are. If you remember, this is a natural log. So we can write this. This is quotient rule. And so before I take the derivative, I'm going to rewrite it. I'm not even going to do y prime yet. I'm just going to do the natural log of 1 plus e to the x, quotient rule, minus the natural log. So I'm expanding it, in other words. E to the x. Okay, that's the worst e in America. Sorry. Okay, so now what I want to do is take the derivative. So I do y prime, and this is 1 over, because it's the natural log, 1 over 1 plus e to the x times the derivative of the bottom, which is e to the x, minus 1 minus e to the x over negative e to the x, right? Well, a negative times a negative is a positive, so you end up with this. These are not common denominators, so there's a whole lot of algebra that you could do to get a common denominator and then multiply and get add them together and cancel out everything, and you can do that if you want to. This is sufficient here for what we want to do. We can't leave behind the fundamental theorem of calculus, and so here we have a function. This is our big Fx. Which is the integral of 0 to e to the 2x of the natural log of t plus 1 dt, and we want to find the derivative of big Fx. Okay, so remember that we write the function just like it is, and where there's a t, we're going to put in the number that it has up here, e to the 2x plus 1, and then we're going to multiply times the derivative of e to the 2x. Well, that's going to be e to the 2x times 2. So big Fx, so the derivative of the integral, is going to be this. So once again, since we're using the derivative, we're going to be doing the applications of a derivative, and that's finding the equation of the tangent line to this curve that's given, at this point. So remember that the first thing you do when you're looking for the equation of the tangent line is that you need a point and a slope. And remember, if you'll associate the word slope with derivative, right, that means that we're going to take the derivative of this function. So it's going to be e to the negative 2x plus x squared times the derivative of the exponent, which is negative 2 plus 2x. All right, so we need the slope at this point, so we want to substitute x equals 2 into this equation. So I'm going to have e to the negative 2 times 2 plus 2 squared times negative 2 plus 2 times 2, which is 4. All right, so this up here is negative 4 plus 4, which is 0. And remember that e to the 0 is not 0. It is 1. Remember, e to anything to the 0 power is 1. So 2 times 1 is 2. So that is my slope. My slope is 2. So using point slope form, which I need a point, which is 2, 1, and a slope, which is 2, then I have y minus 1 equals 2 times x minus 2. Now, you know, if for some reason you need it in slope-intercept form, it's quite easy to do that by just moving it around algebraically. All right, moving on. Okay, on the next example, we're going to find the derivative using implicit differentiation. All right, so we're going to start left to right, taking the derivative as we go. So I have e to the xy. So I know that's going to be e to the xy times the derivative of the exponent, which is the product rule. So I have first, which is x, times the derivative of the second, dy dx, plus the second times the derivative of the first, which is 1. Then I have the derivative of x squared is 2x. The derivative of y squared is 2y dy dx. And then the derivative of 10 is just 0. All right, so the goal is to get the dy dx on one side and anything that's not dy dx to the other. But I have these parentheses, so the first thing I'm going to do is I'm going to do e to the xy times x dy dx. I'm going to go ahead and distribute, plus y e to the xy plus 2x minus 2y dy dx equals 0. All right, and then any term that doesn't have a dy dx in it, I'm going to move it over to the other side. Okay, so I'm going to put an equal sign here. If I move them over, it will be negative 2x minus y e to the xy on one side. Okay, and then on the other, I have this term with a dy dx in it, and I have this term with a dy dx in it. So I'm going to go ahead and just leave those over here. So I have x e to the xy dy dx minus 2y dy dx. All right, now I'm going to factor out the dy dx from these two terms, which is going to leave me x e to the xy minus 2y. Can you hear how deliberate I'm being? There's a lot of x's and y's and e's in here. 2x minus y e to the x. And I don't have anybody over my shoulder telling me whether I'm making a mistake or not. So I'm trying to be very, very careful. All right, so then I'm going to just divide this whole thing to the other side. So rewrite the top. Now sometimes, since they're both negative, you'll see in an answer book that they'll factor out that negative and just write it once out in the front. I don't know why they do that, but that's what they do. I'm not going to. It would require that I would write it yet one more time. And so this, my friends, is your answer. Now, I love these. Don't these look really complicated? But if you'll just be very deliberate, it turns out really well, and it looks awesome, and it looks amazing on your paper. Be sure and show your parents this is what you did. Okay, this is the final example on this video, and we're going to try to find the relative extrema of f of x equals x times e to the x. So the first thing that you do when you're looking for extrema, which is a max or a min, relative max or min, is to take the derivative and set it equal to 0. So that's what we're going to do first. We're going to take the derivative, which is the product rule. So once again, first times the derivative of the second plus the second times the derivative of the first. Okay? And then as I set this equal to 0, I think I'm going to go ahead and factor out an e to the x as I send that equal to 0. And then this can never be 0. That will never be 0, never, because there's an asymptote there. So really what I need to do, I can divide it by e to the x, but I know that x is going to equal -1. So I'm going to have a relative extrema at -1. Set up a little sign chart. I like my favorite 0 and then -2. And then since I got this from the derivative, that's what I'm going to plug 0 and -2 back into, the derivative. So if I put a 0 back in here, I get 0 e to the 0 plus e to the 0. E to the 0 is just 1, so this is positive. If I put a -2 in, -2 e to the -2 plus e to the -2 is going to be -2 over e, so this is negative, plus a little bit more, so this is going to be negative. All right, so since it decreases on the left and increases on the right, we can see here that there is a relative minimum at x equals -1. And if I want to know what the y-coordinate is, I go all the way back. I want to know what f of 1 is, f of -1, sorry. So that's going to be -1 e to the -1. So this will be -1 over e. So I have a relative minimum right here. And that's how we do that. So I hope you took good notes. This is the same applications that we've been doing with derivatives all this time. So it's not new stuff, it's just using e to the x and natural log. All right, so I shall see you in class.